All right, welcome back, everybody. This is day 2 of 4.6 motion. We're going to answer a bunch of questions about a polynomial. We're going to find the velocity and acceleration functions, the position, speed, velocity, and acceleration at a specific spot where t equals 2. At what point is the particle stopped? When's the particle speeding up and slowing down, just like we did with the graphs? Find the net. Net distance might be negative, so watch out for those. Find the total distance traveled. Total distance traveled always has to be positive. From 0 to 5, that specific span. And then we're going to draw a schematic picture of this motion. All right, here we go. Part A. That's one of my favorite parts. Take the derivative of the position function to get the velocity function. So the velocity is just one derivative away from the position. Take it out, multiply it around, and there's the velocity function. The acceleration function is just one derivative away from that. One derivative away from that, we get a constant. So the acceleration is always positive. That's part A. Find the velocity and acceleration functions. Now we want to find the position, speed, velocity, and acceleration at t equals 2. So now we're going to let t equal 2 for part B. We need to find the position at B. So that is s of 2. Shove a 2 in there and see what you get. That's 8 minus 16 plus 11 more, negative 8. I get 3. So the position when the particle at t equals 2 is 3. Maybe meters, and it always compares to the origin. How about the velocity? What's the specific velocity at t equals 2? So you put that into your velocity machine. The velocity is 0 at t equals 2. That means this particle is stopped. Let's find the acceleration at t equals 2. Shove that 2. There's no place to put it. So the acceleration at t equals 2 is 4. Is that okay so far? We have to find one more value there. It says find the speed at t equals 2. The speed is always the absolute value of the velocity. So in this case, the speed is the absolute value of 0, which is 0. It stopped, so its speed is also 0. At what point or points is the particle stopped? Part C. Part C is where we set the velocity machine equal to 0 and solve. We want to know where the particle is stopped, and that's where it has no movement. So set the velocity machine equal to 0 and solve. Just like you suspected from part B, at t equals 2, the particle is stopped. Part D, when's the particle speeding up and slowing down? This is where we have to compare the nature of the velocity and acceleration, just like we did yesterday on those graphs. So we need to find what intervals do the velocity and acceleration have the same sign, and what intervals do they have opposite signs. So this goes back to the first couple of days that we were learning the derivatives. We used to call this the slope of the tangent line testing number line. It was one derivative away from the original. Now we're going to call this the velocity number line. We set the velocity equal to 0 to find all the critical values. So this 2 is a critical value. We put it on this velocity testing number line. Then we want to test numbers to the left of it and to the right of it. When you plug in numbers like t equals 0, you're going to get -8. So the velocity is negative leading up to t equals 0. That means this particle is moving left for the first 2 seconds. We put in numbers beyond 2, like 3 or 10 or whatever is easiest for you, and you get positives. Or note that the signs will change on roots of odd multiplicity. Since 2 only occurred once, we knew that the signs were going to change. That is the slope of the tangent line testing number line. Now we're going to refer to it as the velocity testing number line. Now we need an acceleration testing number line. We used to call this the concavity test, but now it's called the second derivative or acceleration test. Set the second derivative equal to 0 and solve. You can't. There are no critical values based on the second derivative, and that's why this problem is kind of bizarre. The acceleration is always positive 4, so the acceleration is always positive. Now here's the trick. This is what our number lines would look like when we're just testing the slope of the tangent line and the concavity. But when we're testing for speeding up or slowing down, we need to add a couple more values. 0, t equals 0 is not a critical point. Neither derivative produced 0. However, t equals 0 is where we start this experiment. So we don't even want to consider the t values that are negative. We don't care what was happening to the particle prior to this experiment starting. Then it's kind of hard to see. I covered up one of my negative symbols. So I just riddle this zone with negative values. And then beyond 2, the velocity is positive everywhere else. And then I riddle this one also. Each interval, I want to put more than just one testers. I put a vertical line through each one of the critical values, and now I can make my determination. The velocity is negative here, and the acceleration is positive. They have opposite signs, the particle slowing down. Positive velocity, positive acceleration. On that interval, it is speeding up. So where is this sucker slowing down? It's slowing down on the interval from 0 to 2. So my t values have to be bigger than 0, smaller than 2. We don't include the endpoints for speeding up and slowing down because the particle is typically stopped at those spots. To write this in set builder notation, it looks like this. To write it in interval notation, it's slowing down over the open interval from 0 to 2. Where's this sucker speeding up? It's speeding up when the velocity and acceleration have the same sign. It's speeding up when t is greater than 2. Or, if you prefer the interval notation, from 2 to positive infinity. And I hope that makes sense to everybody. Now we're supposed to find the net and total distance traveled from 0 to 5. Let's do the net distance first. The net distance is the distance between where this particle ends and where it started. That's the net distance. Net distance sometimes can be negative if this particle traveled left more than it traveled right. So the net distance for part E, it's my second favorite part. It's the position at t equals 5 minus the position at t equals 0. We have to throw 5 into that position function. So throwing a 5 into the position function, it looks like this. Then we throw a 0 into that position function, and when we do that, it looks like this. Some of this stuff you guys probably can do in your head. So when we put 5 in there, that's 25. 50 minus 40 plus 11. 50 minus 40 is 10 plus 11. Then we're talking about 21. Minus gone, 11. So far, so good. This particle has a net distance of 10. Now let's find the total distance traveled. The total distance traveled is more complicated using algebra. And until we get to the next section, we're going to have to use algebra to find the total distance traveled. So the total distance traveled from 0 to 5, I have to figure out how far it's traveled to the left and then take the absolute value of that distance. And then how far has it traveled to the right? So if we look at just the velocity number line, we're going left from 0 to 2. We need to figure out that left distance, and it's going to be negative, and we're going to have to negate it. It's kind of like driving to Steak and Shake and then coming partway back and stopping at Big Lots. Okay, that's the idea. We're going towards East Peoria, and then we're coming back towards Washington. That's the idea. So here we go. Let's find the total distance traveled left over the span from t equals 0 to t equals 2. To do that, we just shove her in. Fortunately for us, as long as I did it right the first time, this should be the distance. Nope, that has nothing to do with it. This should be the distance from 0 to 2. It should be 11. Let's find out. Send a 2 to that machine. Minus what you get when you send a 0 to that machine. Well, 2 had nothing to do with either of these, did it? But when I send a 0 to that machine, that's where we got that 11. 4, 8 minus 16 plus 11. That's 3 minus 11. That is negative 8. This particle travels 8 units to the left in the first 2 seconds. We need to take the absolute value of that. We're only interested in the distance traveled, so that's 8. Now, we need to find the distance traveled to the right. The distance traveled to the right, according to our velocity testing number line, is the position that we stop at. In this problem, it's 5. And the position where we start from, and in this problem, going to the right, we start at t equals 2. We're trying to find the total distance traveled here, or what's abbreviated TDT. Send a 5 to that machine. Already did it. Send a 2 to that machine. I think I already did it. So 21 minus 3, if I've done those computations properly, is that 18? That's how far this sucker has traveled to the right. We traveled 8 units to the left, 18 units to the right, a total distance traveled of 26 units. Now, depends on what the function's in terms of. Might be meters, might be feet, miles. 26 units. I hope that makes sense to everybody. If it doesn't, make sure you email me and ask some questions. But here's the idea. It's a good system of checks and balances for this problem. If I traveled 18 units to the right and 8 units to the left, can you see what my net distance traveled would be? You subtract all the left movement from all the positive right movement, and the net distance traveled should be 10. I hope that makes sense. It's a good system of checks and balances for these problems that we have to do algebraically. And the last question there, it says, draw a schematic picture of the motion. A good example of schematic drawings is on page 293 of your book. Let's do it here. I'm not sure if you guys do this in physics class or not. If you don't, you'll do something super similar to this. So part F, drawing a schematic picture. A schematic drawing of this is, we have a position number line, and we want to highlight all the critical values on that number line. Critical values come from the first and second derivative test. So we want to find all the t values that are critical. And we want to plot them and find all the positions at those critical values. Remember, the AP test writers, instead of S, they call this X for position. Although we didn't get this value from calculus, it's one of the critical values. It's when the experiment starts. They want to know, where is the particle at the beginning of the experiment? Then now we have to look back up. We have to look back up and see, what are our critical values? The critical value from the first derivative test was t equals 2, and the critical value from the second derivative, or the acceleration test, there was none. So we need to plot where t equals 2. We put all our critical values on that list. Sending 0 to the position function. Again, make sure that you send it to the right function. This, we want to know its position. When you do that, you get an initial position of 11 units. So it's 11 units to the right of the origin. Shoving in t equals 2. When you shove in t equals 2, you will get the position at that. It feels like I've already done that somewhere. You get a position of 3. If you want to use your calculator and look at the tables, feel free. Let's plot those points. On the position function, we're plotting 11. On the position function, we're plotting 3. The next example will have a few more critical values to plot. Then, the idea of the travel of this particle, for the first 2 seconds, it's going left. So this particle starts at 11 and goes left until it hits 3. It's slowing down along the process, and then it hits 3. As soon as it hits 3, it turns and changes direction. It goes back to the right, and it's speeding up. And so it goes like this forever and ever and ever. The problem with showing that on the position number line, or the position continuum, is it's hard to tell which direction that we are going for the this particle. Again, starting at 11, and we're slowing down until we get to a stop. Then we're speeding up and going for eternity. To show this with a schematic drawing, we just hover up above that axis. And here we are at t equals 0. We have to label all these critical points with their t values. We're going to the left, we're slowing down, and then instead of overriding this and going back, I can't really see that, we hover up above that. And we turn around and we go the opposite direction. Again, the actual movement of this particle is left and then right. To show it pictorially, we raise it up, we hover above that axis, and we go left. We have to put some directional barbs on here. The minimum requirement for when I grade them is you just have to have one, and there it is, not including the final arrow tip. I call these little dudes the directional barbs, and now we're going this way. I put a directional barb on every different turn. We have to label the time in which the position was 3, or when it changed from negative velocity to positive velocity, and that was t equals 2. And then we have to indicate where this particle is speeding up and slowing down. In our book, it uses blue to indicate slowing down. In our problem, we have to put this legend, and slowing down, unless you want to use colored pencils, for me, is going to look like railroad tracks. And speeding up, in our book, speeding up is red, but for our legend, speeding up is going to be a solid line. So this sucker is slowing down from 0 to 2 and speeding up from 2 to eternity. So slowing down, does it make sense that something has to slow down before it stops? And then speeding up and never looking back. That's it. Those are the minimum requirements. Plot the values on the position function. Plot the values and list the times of all these critical values, including the start of this experiment. Figure out where it's speeding up and slowing down, and you got her made. I hope this makes sense. Again, email me if you have any questions. The homework assignment now on this one, I believe, is page 294. Six, 9 through 12, 17, 18, and 20, and then the 3 schematic drawing problems are 25 through 28. Now, I hope you enjoyed this lesson, and good luck doing your homeworks. As always, stay healthy.